Alright, welcome to Chapter 6.3. So just to remind you, in Chapter 6.2 we talked about how to simulate studies comparing two means. So in Chapter 6.3 we're going to talk about how to accomplish the same task using the theory-based approach. We're going to start with an example, but for any theory-based approach, we need basically two things: validity conditions and a formula to calculate the standard error. So keep your eyes out for those two things because that's the big takeaways from this chapter. As a side note, I am making a renewed effort to use the presenter notes for these slides. So if you are looking at the HTML slides in the browser, you can hit P and get an approximation of what I'm saying written out. If you think that will save you time, rather than listening to the videos, by all means go for it. I try not to be quite as snarky in the notes on the slides as I can get when I'm actually talking about them. So, let's get started. There are many studies out there that examine the effects of breastfeeding on any number of long-term, down-the-road factors. So things like asthma rates, intelligence, gut bacteria levels, obesity, early death, dementia, those sorts of things. In this particular study that was published in 1999, researchers recruited mother-infant pairs from hospitals in western Michigan, and I'm assuming due to the demographic limitations of relatively rural Michigan, the study involved only white infants and infants born in 1980 or 1981. After signing up all of these mothers and babies for this study, the researchers looked at the demographics of the surrounding counties and determined that the people in their study were a reasonable representation of the surrounding communities. So, quickly on your own, think through the answers to the following questions. Test yourself. These are exactly the kind of questions that I'm going to give you on an actual test. So go ahead and pause the video, and when you think you have the answers, go ahead and continue. Alright, so the answers. This is an observational study, it is not an experiment. And we know that because the investigators didn't get to assign treatments, breastfeeding or not, to the infants. That's a decision that mama gets to make. And it's pretty unethical to just randomly assign breastfeeding or not. It's also pretty impractical. Not all mothers can breastfeed successfully. Not all infants can tolerate formula. Not all infants can tolerate breast milk. In general, it's pretty hard to do experiments on infants because there are a ton of ethical considerations that get in the way. So, this is an observational study. Similarly, infants were not randomly selected from the population, so this is not a random sample. Again, you've got to get consent from the participants in the study. And so you can't just randomly choose people from the population and force them to respond. In addition, it's pretty hard to get a full survey of all infants in an area. You can get information about everyone who's registered with Social Security or every birth certificate that's filed with the state, but that doesn't necessarily guarantee that the infant lives in the area. So some of the random sample get a full list of everybody in the population. those things are pretty hard with newborns as well. So, not a random sample. People were volunteers. They were recruited. The next question is it a representative sample? And the researchers have made some attempt to argue that it is. They took their sample, compared the demographics to the demographics of the local population, and if you trust their assessment of the demographics of the region, and you're not trying to generalize to groups other than white infants in Western Michigan, then maybe you're okay. But, especially these days, things were a little looser in the 80s in terms of what you could get away with publishing, but these days, I don't think a study like this would pass muster if the researchers were attempting to generalize to even all infants in Michigan or all infants in the US, let alone infants worldwide. There's just too many other factors that get in the way. So cultural stuff. You've got only white infants, so there's some racial generalizations that you can't reasonably make. There's medical standards that don't generalize to other areas. There's environmental factors. There's too many other things that get in the way. So, because this is not an experiment, we're not assigning treatments to groups, we can't make any sort of causal conclusions. There's no random assignment of treatments to observational units, and there's always the possibility that mothers who are more educated or more scientifically literate are more likely to breastfeed. That might be true now. I know that that's a significant issue in more modern breastfeeding studies. Back in the 80s, the recommendations were different, so it might actually be that people who are more well off and who can devote more attention to their children such that they would perform better on an intelligence test might have been able to afford formula. We don't know, but there's always the potential for a lurking confounding variable. So, in this particular study, all we can say is that there's an association, or all we might be able to say, rather, is that there is an association between the method that the mother uses to feed the child and their intelligence, at best. All right, so the researchers followed up with the children at age 4 because it's very hard to give an infant an intelligence test. They're nonverbal, they're squirmy, they don't have any attention span. It's better to wait. So they recorded their score on the General Cognitive Index, which is part of the McCarthy Scales of Children's Abilities, and then also recorded whether or not the child was breastfed. And presumably there were some criteria in terms of the length of time the child was breastfed. Don't know. But go ahead and take a minute and think through what the researchers would be using as their hypotheses, and just go through the words at the moment. Okay, pause the video, and when you're ready, unpause it. Alright, so the null hypothesis I came up with is there is no underlying association between breastfeeding during infancy and score on the GCI at age 4. The alternative hypothesis that I came up with is that there is an association between breastfeeding during infancy and score on the GCI at age 4. So, the next step would be to write those same hypotheses in symbols. So go ahead and pause the video. Take a moment to do that. And unpause when you're ready. There are 2 equivalent ways to write this. You can write things out as the difference in the 2 means. So the null hypothesis would be the difference in the 2 means, the population mean of the group of breastfed infants minus the population mean of the group of not breastfed infants is equal to 0. And the alternative would then be that the difference in those population means is not equal to 0. I'm more fond of the little bit simpler hypothesis of the population mean GCI score of breastfed infants, so mu BF, is equal to mu naught, and the corresponding alternative hypothesis of population mean of breastfed infants is not equal to the population mean of not breastfed infants. So this is very similar to chapter 5, but again, make sure you're using mu because this is a quantitative variable instead of using pi, which would be appropriate for categorical data that is summarized as a proportion. The book doesn't give us the full data for the study. The authors of the book may not have had the full data, but they've provided enough sample statistics that it's relatively easy to simulate data. Here you can see that the entire box plot for breastfed infants is shifted just slightly over. Not a huge difference, maybe a couple of points from the full box plot of infants who are not breastfed. But the other thing that would be useful to notice here, and you can see it on the graph as well as in the table, is that the number of infants who were breastfed is a lot bigger than the number of infants who were not breastfed. That's just something to keep in mind going forward. Okay. So we've got our data. The next step would be to, let's say, computer confidence interval. Let's estimate the size of that difference in group means instead of graphically kind of eyeballing it. So one method, which I've kind of termed the theory-ish confidence interval, is to use the simulation data, or rather, simulate the whole study over and over again. So I did it 1,000 times, and compute the standard deviation of that mean difference from the simulation. So this 1.815 here, and use that in our confidence interval. So that's cheating a little bit. You don't have to actually calculate out the standard deviation of the statistic, so the standard error. You can just grab it from the simulation. But because it's simulated, you're assuming that the null hypothesis is true. And that's probably not a big deal, but I can see where it could be a problem in edge cases. So if there are maybe differences in variability between the two groups, as well as differences in means, and maybe differences in group size on top of that, maybe it would be a problem. I don't know. But by far the better option is option 2, which is to calculate the full-on theory-based confidence interval using the formula for the standard deviation of the mean difference. So the standard deviation of the mean of group 1 minus the mean of group 2. And if you're looking at this formula, it should give you some flashbacks from the proportion chapter. Instead of p times 1 minus p for each group here, we have s squared for each group, and that is divided by the number of items in that group, but otherwise the formula looks pretty similar. We can plug everything in from the table and get a standard deviation value that is 1.787. If we flip back, that's relatively close to the simulated standard deviation that we got. It's probably not going to make a huge difference. Our interval is relatively close as well. On the test, on the quizzes, use option 2, calculate the standard error use the formula unless you're explicitly told to use the simulation standard error. The reason for that is so that I know that you can calculate that standard error, and also so that everybody gets the same answer. Okay. We've got a formula for a confidence interval. We can take our standard error and just as easily compute a standardized statistic. So we're using t here because we're dealing with quantitative variables. We've got our statistic minus the hypothesized value divided by the standard error. Looks peachy. I promised you that I'd give you a formula for a standard error and the validity conditions. And just like with the validity conditions in Chapter 3, we have two options. If both groups have a symmetric sample distribution, then we can proceed with theory-based inference. Or if both groups have at least 20 observations each, and the sample distributions aren't really highly skewed, then we can also proceed with theory-based inference. Both of these are designed to ensure that the x1 bar minus x2 bar quantity is normally distributed. So if the validity conditions hold, you can use the guideline that if you get a standardized statistics of more than 2, the p-value is most likely less than 0.05. Therefore, you can conclude that there's evidence against the null hypothesis and reject it and conclude that the alternative hypothesis is a more probable explanation. With every theory-based chapter, we've talked about factors that affect the width of a confidence interval. Nothing has changed here. The number of observations you have affects the confidence interval. If you have more observations, you have a narrower interval because you have a smaller standard error. But because we have two groups now, we not only have the total number of observations to consider, we also have the balance between the two groups. So if you've got very few observations in one group and almost all of your observations in the other group, that's going to lead to a higher standard error of the difference between those two groups than if you have completely equal group sizes. So the more balanced, the smaller the margin of error, the narrower the confidence interval. The higher the n total, the smaller the margin of error, the narrower the confidence interval. Other factors include the variability of the groups themselves. And both group 1 and group 2 factor into that. So if there's more variability in your data, then your confidence interval is going to be wider. Makes sense. The last factor that affects the width of the confidence interval is the multiplier, and that's in this class always going to be 2. So that particular factor, you just have to know that it exists. With that, we are done with Chapter 6. So, congratulations! You've survived the first full chapter that we have done online. I hope everybody is doing well, and this is my perpetual reminder that if you have any questions over this material, please feel free to send me a message, ask to have a Zoom meeting. That's in lieu of office hours. I'm not trying to keep regular office hours because I know that there are many people in the class that are not in Central Time, but I would very much love to answer any questions you have about this material. And if you're not comfortable setting up an in-person meeting, post to the discussion board, send me a message.